That it's a pleasure to introduce Andreas Thom from Dresden, who will tell us about finitely approximable groups.
Okay, thank you very much for the introduction. I want to thank the organizers for inviting me here back to Cambridge. I spent a year here when I studied so the part 3 of the mathematics education, like about 17, 18 years ago, and that's the first time I come back. So I really appreciate that opportunity. And I will speak about finitary approximation properties of groups. So there's some overlap in the definitions with the talk we had in the morning by Gulnara, but I think it's okay to see some of the definitions again, I think, and maybe also some different aspects of this whole story. And I want to start with the applications. So why are we actually interested in sofic groups? Why do we want to prove that many groups are sofic? And I will start, so that's the outline of the entire talk, with some background on equations over groups. So that's a classical topic in group theory, and it goes as follows. So gamma will typically be a countable discrete group, and you have, well, is that working? Okay. You have a couple of elements in the group. You have a number of integers, so these are exponents. And you look at this combination, so T is as a formal variable. You look at this equation over the group, and you say that this equation has a solution in the group gamma if there exists some element h which solves this equation. So you insert h for T, then you can compute everything in gamma, and maybe the result of that computation is the neutral element, and then it's the solution to this equation. And typically it will not be the case. So I mean, if you have like a typical discrete group, then there are many equations which are not solutions. But as you learned it in algebra, sometimes maybe there is an extension where suddenly something has a solution, like in the theory of fields, where polynomial equations may not have solutions, but in the field extension they always can be solved, I mean, under suitable, well, weak kind of assumption. So what you're looking for is maybe not a solution in gamma, but what you're looking for is a bigger group. So you're looking for a solution over gamma, which means that you can extend the group to another group, which then contains an element so that that solves the equation. So that's kind of maybe a more reasonable question to ask. And that has been asked a long time ago, where basic equations were studied. And so I think the state of the art is that it's pretty unclear what are the exact abstractions. So I will mention a few conjectures in this context, which are very nicely looking, very nice conjectures, and but they are, it's possible to prove them for sofic groups. So, and it's unclear whether they hold for all groups or whether there's really an abstraction. So one of these fundamental problems.
You only consider one equation, like right? You can also consider several equations, right?
Sure. Yeah. You can look at n variables, k equations. You can ask the same question. I mean, this is the simplest case, right, that I want to mention here. I mean, everything I say about equations can be extended to systems of equation and so on. And then, right. So, but let's look at some simple examples. So, if you have two elements a and b, and they are of finite order, then having a solution to this type of equation that implies that the order of a and b have to be the same, because if this is trivial, then I mean, a will be conjugate to the inverse of b, and even if that is true in an extension of the group, it forces the order of a and b to be the same. So you cannot just expect that any type of equation will have a solution in a bigger group, right? Right. So this is the argument, right? If such a solution exists and they are conjugated, that of course forces the orders to be the same. So that's if you have different types of torsion, but in fact, there's a slightly more complicated example where you just have one equation and you have just one type of torsion, and still this equation is not solvable, not in the group, but also not in any extension of the group, right? So even if you have just one type of torsion, such an equation cannot be solved in general. So why is that the case in this example? It's a nice also classical argument. So suppose there's a solution to that equation, then, well, writing it a little differently, a square is conjugate to a by some element which itself is conjugate to a, right? This is this TAT inverse. And if A is conjugate to A squared, so you remember A has order P, then the conjugation of this by this element, it has to induce an automorphism of Z mod P, which sends 1 to 2. And since this has to be multiplication by 2, and we know that the order of this is by classical number theory, absolutely basic number theory, must be a divisor of P minus 1, and then in particular cannot be conjugate to A, which has order P. So you can just of one type of torsion construct two types of torsion which kind of interfere in a bad way, so that it's complicated to solve general equations in the presence of torsion. And so you may observe from these two examples that torsion is a problem, and another problem is that maybe it's a little bit special, the situation that the sum of the exponents is equal to 0, right? That one would expect that maybe that's a special case that one has to understand in a kind of like a different methods. So here also the exponents add up to 0. So we say that an equation is non-singular if exactly this sum of exponents is not equal to 0. These are equations which we hope behave better than general equations, and we call I mean, there's another reason why equations might be difficult to solve. So if it's just conjugate to a constant, right, then you can also not solve it. But that's kind of clear, right? So first of all, there's one conjecture, classical conjecture, which says that this very weak obstruction to solvability is the only one if the cube is torsion-free, right? So there are no counterexamples to this, so maybe that's true. And then there's another conjecture coming from low-dimensional algebraic topology, that under this slightly stronger assumption that this equation is non-singular, then even if the cube has torsion, there's always a solution, right? So that's maybe, I mean, from my point of view, this is maybe the more natural one, or at least, both conjectures are really, really nice. And so what we know is, I mean, there are a lot of results in that direction for particular equations, but the really most general result, or the most striking result in some sense, was proved by Anton Klyachko, and he proved that, if both conditions are satisfied, if the cube is torsion-free and the equation is non-singular, then indeed this can be solved, right? So this was famously published in an article, A Funny Property of Sphere and Equation over Cube. So that was hard to read, I can say. And but this is it's a very combinatorial approach using diagram techniques, geometric and algebraic. So, so this is basically the state of the art for these two conjectures. There are other results, but in this generality, this is I would say, the most striking result. So I will focus on the second conjecture because that is now something that that is related to this class of sofic cubes. And so why is this problem complicated at all? I mean, for fields, the solution is easy. If you don't have a root, then you attach a variable and solve the equation. So why don't you just attach a new variable and divide out your equation, right? So there you have the cube which contains a solution. Well, the problem is that if that is a general equation, then it's very complicated. In fact, that's the entire difficulty to show that this map is injective, right? So this looks very innocent. I mean, it's after all the free product, and you divide out something which contains t in a significant way, right? It has degree not equal to 0 in t, but still, if you think more about this problem, it's not clear how you would prove the injectivity in general. And yeah, and that's in fact the only problem, right? I mean, it's this is not. I mean, if you think about it, the injectivity of this map is the exact problem that you have to solve. So if algebra and combinatorics does not help you, then maybe sometimes topology helps you. And in this case, there was a famous result of Gerstenhaber and Rothaus, which said that if you have a non-singular equation, as I said, so the total degrees of in the t's is not equal to 0, and your coefficients in this equation are unitary matrices, then you find a solution to this equation in the unitary group. And that's using just the basic degree theory of maps between manifolds. So you can compute exactly what is the degree of the map that is induced by this equation, so mapping t to w of t. And you prove that this degree is non-zero, and then the map must be surjective, so it must hit the neutral element, and any pre-image will be a solution. So it's a completely inexplicit argument, and even if you're, I mean, for example, even if your constants that you're putting into the equation are permutation matrices, there's no way to give a reasonable bound on where this solution lies, right? So this solution might be, it's just coming out of kind of a fixed point argument or a degree type argument, and it can be a priori very complicated. Anyway, this implies that if you have a non-singular equation with coefficients in a finite group, then you can solve that equation over this group, because after all, this finite group can be put into a unitary group, find your solution there, and well, that's the group which contains the solution. And if you are, well, thinking a little bit more, then you can even prove that this can be taking a finite group by using that finitely generated linear groups are residually finite.
So why do you call the condition non-singular? Is that some underlying space?
Non-singular was this condition on the sum of the exponents of the variable.
Yeah. Why do you call it singular? Non-singular.
Well, because if something is 0, then sometimes you call it singular, and in this case it's non-singular. This sum of exponents is non-zero. There's no deeper thought, it's just...
So there is no underlying space on the right?
Well, no. It's a countable set of equations that you look at, and there are some which have a non-zero sum of exponents, some have a 0 sum of exponents. Okay, so that's the... And of course, if you think more about it, you can prove it for locally residually finite groups and all kind of groups which are close to finite groups. But it's in fact true for sofic groups. And that follows from, I mean, once you know that, once you know it for the unitary group, you basically know it for many more groups. So if you look back at this result, so you could call the unitary group algebraically closed if any equation can be solved, right? That seems like a reasonable notion that you can now attach to this group. It's algebraically closed because all equations can be solved, so a bit like the complex numbers. And once you know that, it's pretty clear that products of algebraically closed groups are algebraically closed. Quotients of algebraically closed groups are algebraically closed, basically because you just, while products is clear, you solve in each coordinate. Quotients is also clear because you lift your equations, solve, and map the solution down. So these are elementary observations, but they lead you to a really non-trivial corollary, which was first, I guess, I don't know exactly, observed by Vladimir Pestov. So if your group gamma embeds into an abstract quotient of a product of unitary groups, right? That seems like an absolutely weird condition to ask for, but definitely then this conjecture that I mentioned about the solvability is true for your group gamma. And this abstract quotient, this, for example, could be exactly one of these metric ultra products that Gulnara defined in her first talk. So you take this product and you divide out some normal subgroup of 0 sequences, and if your group embeds into this quotient, then it will satisfy this Kervaire conjecture, right? And I will not speak about these hyperlinear groups, but a sofic group can be embedded in such a product, in such an abstract quotient of a product of unitary groups. And I will review the definition of a sofic group and also explain maybe in a few words why that can be embedded here. So that's how you use this condition to be sofic. And you basically use it to see that your sofic group embeds into some algebraically closed group and then find your solutions over there. So what was a sofic group? So, well, a sofic group, you first have to I have to review the definition of this normalized Hamming metric. So if you have two permutations acting on n elements, then you, in a normalized way, look at this Hamming distance. You look at the points, so this should go from 1 to n, I guess, where they are different, and then you divide that by n. So this will be a number between 0 and 1, a real number. And it gives you a good distance function on the symmetric group, and it's important to normalize it because you really look at the entire family for all n and not just at a single group, right, where this is like a discrete metric anyway, right? So as n increases, the distances can become smaller and smaller, and so this gives you a lot of flexibility if you want to talk about these approximation things. So now a group is called sofic if for any finite subset of the group, right, Gunara took balls of radius n, but you can formulate it easily also in this way, finite subsets, and for any epsilon between 0 and 1, there exists some n so that you can map your group into the symmetric group on n points in a way which is almost a homomorphism, right? It's almost a homomorphism on the set F, where you measure this deviation from being an actual homomorphism by the Hamming metric and this epsilon that you put into the definition. And then you also don't want to allow that everything maps to the trivial permutation, so you also want to say that, well, every non-trivial element should move at least a certain percentage of points, in this case 1/2 of the points, but this really doesn't matter. You could ask for 1 minus epsilon, or you could ask for any bigger than any constant delta, even depending on g and so on, but it has to be, well, there has to be some non-triviality condition to make this an interesting definition. Okay, so that's the definition, and so starting from this, you can imagine that now you can, viewing permutation matrices as unitary matrices, can find a map to this metric ultra product. I will also define this metric ultra product later. So sofic groups, they really come from, well, many different sources, and so the two sources are, I mean, the first source are residually finite groups, so this gives you a lot of examples coming from linear groups. Another source is amenable groups, and so, I mean, residually finite groups, that's really obvious because you can map it to the finite quotient, and then this will be acting on itself by permutations. By amenable groups, it's also very easy. You can act on the Fellner sets in a way which only causes a little trouble at the boundary, so that's also a good approximation in the sofic sense. And then you have various permanence properties that are satisfied for the class of sofic groups that allow you to construct more groups once you have residually finite and amenable groups. And well, in fact, it's not so easy to find good candidates for groups which are not sofic. Well, there's no group known to be non-sofic. So I think it's one of the, well, in the field of sofic groups, it's one of the major open problems, let's say, that one should finally be able to come up with an example of a non-sofic group. And, well, who knows, maybe there is no, but that would be, I think, more surprising at the moment. And, well, so that's a difficult problem. And later in the talk, I will talk about variations of this problem where we can say more, right? Where we find groups which are non-approximable in a certain sense and relate this to interesting other parts of mathematics where interesting things were going on. So we hope that maybe this will also shed light on this problem, but that's not where we are at the moment. So before I want to continue, I want to say just on one slide something on some work that I did with Anton Klyachko, in fact. So we were looking at the case where you have more variables, right? I mean, you could, as you said, you could look at more equations, and this non-singularity condition, that's already causes some more problems. But what is also a funny thing to do is to look at one equation and two variables where the equation is singular with respect to both of the variables, and then you look for a solution. So that is also should be possible to do, but is difficult from the combinatorial point of view. And so what does it mean? I mean, if the exponents are non-zero in each of the variables, you should still observe that it's kind of non-trivial because the s does not immediately cancel with the s inverse because there's this t in between, right? So it's kind of non-trivial, but in a weaker sense, right? So you have two variables, but if you forget about the constants, it's not completely canceling out. And so we call such an equation non-singular if forgetting about the constants. So an equation essentially is an element in this free product, n variables, so here n is 2. If you forget about the constants, you get only here st, s inverse, t inverse, and then you call it non-singular if that is not trivial, right, like in this case. And so that's our conjecture. If this is non-singular, no matter if n is 1 or bigger, then you have a solution in a bigger group, right? That seems quite natural generalization of this Kervaire problem, and we can prove, well, if this, what we call, I mean, we call it the content, but it doesn't matter. If this element in the free group is not too deep in the lower central series, and your group is sofic, then you find a solution. So there are some extensions, and I mean, my real motivation to prove this theorem is because I liked this argument of Gerstenhaber and Rothaus, this topological argument. I liked it so much that I wanted to extend it somehow to. So here we are using, again, algebraic topology. What we are really proving is that, that equations over SUP, where P is a prime number, can be solved in SUP under some condition on this epsilon W. And the proof uses, I will not tell you the details, it uses more complicated computations in the cohomology of these groups, and we are really using that it's SUP for a prime number P. And, but it's essentially the same strategy. In the end, we prove that a certain map between topological manifolds must be surjective using some topological argument. In this case, we prove that the top degree cohomology class on the right side is mapped non-trivially here by an explicit computation in this cohomology ring. So this is only for the commutator map, but then in the end, everything else can be reduced to the commutator. Okay, that's very quick, but I don't want to spend more time on this part of the story. One more conjecture that is really fundamental. It's over 50 years old. If you have a group and a field and take the group rank, then you would expect that if A times B in the group rank is equal to the identity, then that's also true for B times A. Right? That's Kaplansky's finiteness conjecture. And it's known to hold if the characteristic is equal is 0. But if the characteristic is finite, then it's only known under more restrictive assumptions on the group. And Elek and Andreas Szabo proved it's true for sofic groups. And the strategy is that you use this finite approximation property to approximate your group rank by matrices, and you use that this implication here is true for matrices. So that's the very rough outline, and behind that there are again these ultra products where you carry out this argument. So that's just another source of another application of this concept of soficity, which I think is very nice because it solves this old and famous conjecture under very mild assumptions. So remember, there is no group known to be non-sofic. Right. So this is again the definition of a sofic group. I show it very quickly. So that's a slightly different formulation. What I want to emphasize is that as Gunnar also pointed out, this is a very abstract thing. So we are using a finite group. Well, it doesn't even need to be finite. And we use a metric on this group. And then we set up some approximation condition that either it's satisfied or it's not satisfied, and it defines you some notion of approximability by these particular families of finite groups, maybe with fixed metrics, in this case, these Hamming metrics. So already shortly after this class of groups has been introduced, there was the notion of a weakly sofic group, which would remove all the constraints on the finite groups and their metrics, So you define it basically in exactly the same way, but now you approximate by arbitrary finite groups instead of the symmetric groups, and arbitrary bi-invariant metrics. So I will quickly review what are the exact conditions on the metric that you use. Right. So if now even more generally, if C is any class of finite groups, well, we will call a group in this class is just a C group for short, and then we will consider metrics on these groups which have this bi-invariance property, right? So you multiply from the left or from the right. I mean, in both ways it's invariant, so that's a kind of typically a very strong condition on a group. And once you have, I mean, if you think about such a bi-invariant metric, then you typically only think of the distance to the identity, right? Because that encodes all the information by this formula, but it's putting a constraint also on this length function. It's not just satisfying triangle inequality, but it's also satisfying this conjugation invariance, because you have it on the left and on the right. And that's sort of, well, it's also a strong condition to have a conjugation invariant length function, right? So this will play a role, right? So we adapt this definition and say that G is now C approximable if for any finite subset and any epsilon there exists some map, just some map from S, from the finite subset to your group H, which is in the class C, and there exists some bi-invariant metric on H, so that you have these familiar conditions. Well, 1 goes to 1, you can ignore that. It's multiplicative up to a mistake of epsilon, and it's kind of injective in a very weak sense that you are at least delta away from the neutral element, right? And these, well, such things, you could maybe call them S epsilon delta homomorphism, because that's basically what it is. Okay, so now we can set up a few more conditions. So we already know sofic, we know weakly sofic, and so we will now just fix these classes of groups, so class of finite groups, class of alternating groups, and note that just by definition, weakly sofic groups are exactly the groups which are fin approximable. Sofic groups are alt approximable, but in fact that's already not so trivial. These are exactly the alt approximable groups, because a priori you could look at a different metric on the symmetric group or the alternating groups, but it's a phenomenon that on simple groups essentially there's just one interesting metric. So they are so, I mean, even though the metric is an additional datum, it's essentially fixed by the group structure, which is really a surprising thing. Well, which has this consequence that you don't need to talk about the Hamming distance is kind of coming automatically from the alternating group. So why is that? Well, I mean, there's a very general. I mean, there was also a question about examples of length functions. So if you have, say, a finite group without center, then you can always look at the relative size of the conjugacy class of G, and this formula always defines a metric, and that's in fact on the simple group. It's also it's the canonical metric up to some universal, well, constants that one can compute. I mean, and this is kind of also a very natural metric on many other groups. So that's one example of a length function. We also have we can restrict to different classes or different families of finite simple groups, maybe fixing a prime or not, or there are kind of different things that you can do. So these groups are sometimes called, if they are approximable by these finite groups PSL N Q, they are called linear sofic. Well, okay. Then what are the examples? So, I mean, a lot of things are easy. Groups which are locally in this class, they are approximable. And if they are residually in the class, then they are also approximable. All these things, they come for free. But just to indicate that they are really non-trivial results that use. So I will later speak a little bit about the proof also of this theorem that I'm stating in a second. But it really uses this deep work of Nikolov and Szabo. So we, with Nick and Jakob Schneider, a PhD student from Dresden, we have shown that any group which is fin approximable, so these are the weakly sofic groups, it has a PSL approximable quotient. And so that's kind of, well, first positive result, I think, which would, which relates these different approximation properties and well, uses, and really uses the structure of finite groups that we know. So it uses classification of finite groups, finite simple groups, and a lot more that went into the work of Nikolov and Szabo. So from now on, many of the results that I state are applications of this work of Nikolov and Szabo on commutators in finite groups or finite groups with additional properties. Okay. So that's a short review of these metric ultra products. So you have this family of a family of finite groups, let's say, with these length functions. Then we want to define this metric ultra product, which is a quotient of the product by this normal subgroup of zero sequences with respect to the length functions. This again is a metric group now, because on this quotient this limit is still well defined, so it's a metric group. And from what I just said, it's kind of almost immediate that a countable group, let's say, or discrete group, doesn't matter, is C approximable if and only if it embeds as a discrete group in such a metric ultra product. So that's just restating what Gulnara explained, and that's sort of a more global way to think of metric ultra products, to think of the C approximability if you are not too scared of metric ultra products. So I think I like that viewpoint a lot, because it's not using epsilons anymore, and it's kind of more clean in some way. Well, unless, I mean, of course, these metric ultra products still, they are kind of mysterious, and we are now basically comparing, if you compare different C approximability properties for different classes of groups, we are basically also trying to distinguish these different ultra products for different families of groups. And that's, I mean, if you ever thought about sofic groups, that's kind of complicated, because these epsilon conditions, they are very weak. But still, there's one positive result in this direction that I want to state. That's a result that joint work with John Wilson. We proved that the metric ultra products of different families of finite simple groups, so for example PSL and P and alternating groups, that they remember from which family they came. So if you have an ultra product of PSL and PSL and P prime, for P and P prime fixed and n going to infinity, then these metric ultra products will not be isomorphic to each other. Yeah? And also not be isomorphic to any of the metric ultra products of the symmetric group. So that's much more complicated to compared to this distinction of algebraic ultra products of these simple groups. So if you look at algebraic ultra products of symmetric groups, you can, most of the time, you look at the divisibility properties of certain elements, and then you are able to distinguish algebraic ultra products. But the metric ultra products, they wipe out a lot of this fine divisibility properties, and so one has to come up with new ideas to look at these objects. So they are also geometric in some sense, so, right? So these are topological groups, they have a metric, so in some sense one should look at them from a geometric point of view too. And in other work, also with John Wilson, we proved that all these metric ultra products, at least for these families and also for the other families, but that's a little bit more complicated, they are actually geodesic groups. So they are path connected, and for every 2 points in the group, you find a geodesic path which connects the two groups. Right? So that's not so unnatural for a topological group, but what it exactly means in terms of the finite groups that go into this construction. So it really gives you a new point of view to look at asymptotic properties of finite groups in some sense, right? Because it reflects some structure of the finite group, of course. But okay, so there's some understanding of the geometric properties too. But apart from this, they are in general a little bit mysterious. Okay, so but once you are there, you can now, and that's also something that I want to spend a few minutes talking about. You can also look at topological groups and try to embed them into these metric algebra products, right? And so these metric algebra products, they are metric groups, but the metric is I mean, it's by no means unique, right? It's what I said here is that in many cases the topology is uniquely determined, but the metric might very much depend on the particular choice of metric that you take. So you really should not look at isometric embeddings of a metric group, but rather topological embeddings into such a metric algebra product. Right, and that will induce a metric on your topological group, so it better was a metric group to start with. But what is kind of, for example, easy to see is that under some mild conditions on C, if you have a compact pro-C group, then that should be C approximable, right? And the argument is very easy. You have all these maps to C, and if you combine them all, then you get an embedding into a suitable metric algebra product of these C groups. So all these pro-C groups, compact groups, are C approximable. Our main result concerning these topological groups, and I will state it later and also sketch the proof if I have time, is that SO3 is not approximable by any class of finite groups. So even though that's a very nice, understandable group, it's far away from being even thin approximable, which is the weakest condition that you can ask for. So in some sense, it's a non-sofic group, but it's in a different drawer. It's a topological group, which is not sofic. So that's another result that comes a little bit later. What we have looked at with Jakob Schneider and Nikolai Nikolov is groups that are approximable by finite solvable groups. Right? So that's, of course, a strong restriction on the group. But maybe if you think about approximation by finite groups, then solvable groups, that's kind of a key part of the group, right? The solvable radical is always there, and you should first, before you in general want to prove that something is not thin approximable, look at these groups which are approximable by solvable groups or not. And that was asked by Lev Kaplansky in 16. Are all discrete groups approximable by solvable groups? So that was his question. There were no examples. And our theorem is that as soon as your group is perfect and not trivial, then it is not approximable by solvable groups. So that's a negative result in that sense. So this question has a negative answer. And so even finite groups, if they are not themselves solvable, will not be so approximable. So okay, that's follows from this. And finite generation is important because there are rather weird locally P groups which have properties which are very I mean, they are sole approximable because they are locally nilpotent, but still they do not satisfy this theorem, right? They are sole approximable even though they are perfect, not finitely generated. Okay, and so how are we using this work of Nikolov and Szabo? And so, in fact, I will try to sketch the proof of this theorem here. It uses these results about expressibility of commutators in finite groups. And the first result of that kind was in fact for nilpotent groups, and it's much more classical, so it was the work that was extended by Szabo to solvable groups. But let us start with the nilpotent case. Okay, so I think I'm not in sync with my slides. So I will skip this and well, I think I cannot skip this. So I will quickly show you the general strategy how you would prove that something is not C approximable. Okay, so that's that goes as follows. So if you have a presentation of your group G as a quotient of a free group, then one can show that this group G is C approximable if for any finite sequence of elements in the kernel of this presentation, so in this normal subgroup that you have to divide out, it's true that if you take a product of finitely many conjugacy classes in the Pro-C topology, then you won't get any elements which are outside N. Right, so we will later see how that is applied, and so let me just indicate why this is true. Well, if something is not in N, then and the group is C approximable, then you find some C quotient where this element is mapped to something which is relatively far away from the identity, right? And on the other side, if it's a sofic approximation of your group G, then all these elements which are in N, they are relatively short in this image, because it's an approximation of your group G, and these are supposed to be trivial, these expressions in the group G. And so since this K here is uniform, all these elements that arise in this profinite closure here, they all have a length, because it's bi-invariant, you can take conjugates. They will all be relatively short, and so they should not be containing any element which is longer than, well, this K times some epsilon, where epsilon is the length of the longest of these elements, right? So it's kind of this different viewpoint which allows you to relate this back to the topology with respect to some class of finite groups. And we will use this point of view, so I don't know whether I could make it completely clear why this is equivalent, but maybe we will see later in the proof that how you use it, I mean, how you can argue more concretely with these length functions. So the sketch goes as follows. So you have this finitely generated group, G, which is P, which is perfect, and then you have some element which is supposed to be non-trivial in P, so it's some element outside of this normal subgroup. And since the group is perfect, you can, for each of these generators and also for this element X, you can find elements in N which, modulo the commutator subgroup, are behaving just like the generators. And what we are going to show is that this element X, and this one arbitrary element, will actually lie exactly in the closure with respect to this class for some finite sequence of elements. And so what we are going to do now is to consider an arbitrary homomorphism to a solvable group, and we will construct these elements N1 through Nk independent of the solvable group and show that X is contained in the product of conjugacy classes in this solvable group, in the image. Right, and what we are using is this lemma, which is really somehow the easiest version of all these commutator identities, is that if you have some finite group, then if it's generated by these elements modulo the commutator subgroup, then any element in the commutator subgroup can be written as a product. So these are just sets of commutators. It can be written as a product of elements in these sets of commutators times something in this intersection of the lower central series, which is this gamma omega. So that's a relatively easy kind of commutator expressibility result, but it still tells you that kind of there's some uniform bound, namely in this case it's really R, which comes in. And so we apply this in our situation. We have these elements M1 through MR. We have our element X. And what we conclude from this, that we can write this phi of X as phi of M times the product of commutators times something in this intersection of the lower central series. And you see already from this condition here, if you had a length function in addition, then all these elements, M1 through MR, they are all in the kernel of your presentation of the group P. Also M is there, so they are all short, but this is an arbitrary element X, which then also has to be short, but that's contradicting the condition that if it's not trivial, it must be long in some of these approximations. Okay, so if H were nilpotent, then this would be trivial, and then you would be done. And so if H is not nilpotent, you have to make a longer argument, which I will now not show you, but it uses this deeper work of Szabo. Okay, and then you are basically done, but I will skip this technical argument. So using the same kind of ideas, we are able to answer a few more questions, namely these two. One question by Michal Ducha. He is like a metric model theorist, I would say, and he asked whether all Lie groups, let's say compact Lie groups, embed into metric ultraproducts of finite groups, so the fin approximable, how we called it. And we proved that this is not the case. Such a group has to be abelian if it is fin approximable. Any connected, in fact, yeah, that's also true. Any connected Lie group is fin approximable if and only if it is abelian. So that's what I said. SO3, for example, is not fin approximable. There was also a question by Boris Silber, also a model theorist, who asked whether a group like SO3 could be a quotient of a product of finite groups. So he said that this might be relevant for physics because it's usually difficult to understand Lie groups, sometimes analytically, and so finite groups are just combinatorial objects. But we proved that something like SO3 can also not be a quotient of a product of finite groups. So that was also kind of new result. This, in fact, had been independently observed by Kaplansky as well. So how does that go? Well, again, we use this this enormous work producing commutator identities, which shows that if you have a group generated by H1 through HR, then the commutator subgroup, let's take K equal to H, commutator subgroup is a product of finitely many commutators with the generators. And how do we apply it? Well, I mean, first of all, we conclude that if you have any two elements, G and H, in a finite group, then any power of G, a commutator with any power of H, will be a finite product of commutators of the generators, right? So, okay, so if you think about a condition like this in a compact Lie group, then you immediately see that there are some problems, because if you take two elements that do not commute, but they lie in the range of the exponential map, then you can write them as nth powers, and then G and H will be really, really short. Conjugating or taking commutators will not make them any longer. Then you take a bounded power, will also not increase it by very much. So this will still be very, very short, but here you had your arbitrary commutator, right? So more geometrically, this implies that, I think this is the most significant part given the time constraint, implies that any two one-parameter subgroups of your metric ultraproduct will necessarily commute, right? So these metric ultraproducts, they're very nice. They have one-parameter subgroups, but they all commute, basically because of this structure result and the amount by which two elements do not commute. It cannot increase by taking powers of these elements. So you prove that any commutator is essentially trivial. Okay, I think I had too many slides, I'm afraid. I will just state this other application also of the same kind of idea due to, it was a question by Pillai, if a pseudo-finite group, so that's a limit of finite groups in a different sense, in the sense of first-order theories, whether this can have interesting unitary representations, but in fact all of them are abelian. And the argument is again the same as before, because if you have a unitary representation of such a group, then all the all the sentences that hold for finite groups, they are still true. So in particular, this commutator property that I just discussed holds, and you conclude that the connected component of this Bohr compactification, which is the universal compactification, must be abelian. Okay, I think I was rushing through the last slides, but also to make some more time for the break. So I hope I didn't rush too much. So now I think I stopped 2 minutes too early, but maybe that's not a problem.
Everyone's just going to thank you for that. Does anyone have any questions for Andreas? No, we're going to thank him again really, really enthusiastically for letting us get coffee faster.